In this video, you'll learn about deployment and continuous integration. Deploying back-end applications is a critical aspect of software development, ensuring that developed software is accessible to end users. This process involves transferring the developed codebase from the development environment to a production server where it can be accessed by users. Deploying back-end applications requires careful planning, configuration, and execution to ensure smooth and efficient deployment. In this extended discussion, we will delve deeper into various aspects of deploying back-end applications, including deployment strategies, tools, and best practices. Deployment strategies. 1. Manual deployment involves transferring the codebase and associated files from the development environment to the production server manually. Developers typically use tools like FTP or SSH to upload files to the server. While manual deployment offers control over the deployment process, it can be time-consuming and error-prone, especially for complex applications or frequent updates. 2. Automated deployment leverages deployment automation tools to streamline the deployment process. Tools like Ansible, Chef, Puppet, or Terraform allow developers to define deployment scripts or playbooks that automate various deployment tasks, including code transfer, server configuration, and application setup. Automated deployment reduces manual errors, ensures consistency across environments, and speeds up the deployment process. 3. Continuous deployment is an extension of continuous integration practices, where every code change that passes automated tests is automatically deployed to production environments. This approach enables rapid and frequent releases, reduces time to market, and facilitates rapid feedback cycles. Continuous deployment relies on robust testing and monitoring practices to ensure the stability and reliability of deployed applications. Deployment tools and platforms. 1. Docker is a popular containerization platform that simplifies application deployment by packaging applications and their dependencies into lightweight, portable containers. Containers isolate applications from the underlying infrastructure, ensuring consistency across different environments. Docker containers can be easily deployed to any environment that supports Docker, including development, testing, and production environments. 2. Kubernetes is an open-source container orchestration platform that automates the deployment, scaling, and management of containerized applications. Kubernetes provides tools for defining application deployment configurations, managing container lifecycle, and ensuring high availability and fault tolerance. Kubernetes simplifies application deployment and management, improves scalability, and supports advanced features like service discovery, load balancing, and rolling updates. 3. Serverless computing platforms enable developers to deploy and run applications without managing servers. Serverless platforms automatically scale resources based on demand, reducing operational overhead and costs. Serverless architectures are well suited for event-driven applications and microservices architectures. Best practices for deploying back-end applications include: 1. Use version control systems like Git to manage code changes and track deployment configurations. Version control ensures code consistency, facilitates collaboration, and enables rollback to previous versions if needed. 2. Maintain separate environments for development, testing, staging, and production. Use configuration management tools to automate environment setup and ensure consistency across environments. 3. Implement CI/CD pipelines to automate code integration, testing, and deployment. CI/CD pipelines automate repetitive tasks, reduce manual errors, and enable rapid and frequent releases. 4. Implement robust monitoring and logging practices to track application performance, detect errors, and troubleshoot issues. Use monitoring tools like Prometheus, Grafana, or LK-Stack to collect and analyze application metrics, logs, and events. 5. Implement security best practices, including encryption, authentication, and access control, to protect sensitive data and prevent security breaches. Regularly update dependencies and apply security patches to mitigate security vulnerabilities. 6. Design applications for scalability and high availability to ensure seamless performance and reliability under varying workloads. Use load balancers, auto-scaling, and redundancy strategies to distribute traffic and mitigate single points of failure. Continuous integration, CI, and continuous deployment, CD, are integral practices in modern software development methodologies, facilitating the rapid and reliable delivery of software applications. In this extended discussion, we will delve deeper into the concepts of CI/CD, their benefits, implementation strategies, and best practices. Understanding continuous integration, CI. Continuous integration is a software development practice where developers integrate code changes into a shared repository frequently, preferably several times a day. Each integration triggers an automated build process that verifies the integrity of the codebase, runs automated tests, and identifies any integration errors or conflicts. Benefits of continuous integration include 1. Early detection of issues, allowing developers to identify and address issues early in the development cycle. 2. Faster feedback loops, providing rapid feedback on the quality and stability of code changes. 3. Reduced integration risks. By integrating code changes frequently, CI reduces the risk of integration conflicts and ensures smoother integration with the main codebase. Implementing continuous integration involves 1. Automated build and testing. Implementing automated build and testing processes that execute unit tests, integration tests, and other quality checks automatically whenever code changes are pushed to the repository. 2. Version control. Using a version control system like Git to manage code changes and track revisions. Establish branching strategies and merge policies to ensure code changes are integrated seamlessly. 3. CI server. Setting up a dedicated CI server to orchestrate the CI process. Configure the CI server to monitor version control repositories, trigger builds on code changes, and report build statuses. Understanding continuous deployment, CD. Continuous deployment is an extension of CI that automates the deployment process, allowing code changes to be deployed to production environments automatically after passing all tests. Continuous deployment aims to streamline the release process, reduce manual intervention, and accelerate time to market. Benefits of continuous deployment include 1. Faster time to market, enabling rapid and frequent releases. 2. Consistency and reliability in the deployment process, reducing the risk of human error. 3. Improved feedback loops, providing rapid feedback on the impact of code changes in production environments. Implementing continuous deployment involves 1. Automated deployment pipelines. Defining deployment pipelines that automate the steps required to deploy code changes to production environments. Deployment pipelines typically include stages for building, testing, and deploying applications. 2. Deployment automation. Leveraging deployment automation tools and infrastructure as code practices to automate the provisioning and configuration of infrastructure components. 3. Canary releases and feature flags. Implementing canary releases and feature flags to gradually roll out new features to a subset of users, allowing teams to monitor the impact of changes before fully deploying them. Best practices for CI/CD include 1. Modular architecture. Designing applications with modular architectures and well-defined interfaces to facilitate independent testing, deployment, and scaling of components. 2. Automated testing. Investing in comprehensive automated testing suites to ensure the reliability and stability of code changes. 3. Continuous monitoring. Implementing monitoring and alerting mechanisms to track application performance, resource utilization, and user experience in production environments. 4. Incremental improvements. Continuously refining and optimizing CI/CD pipelines based on feedback and performance metrics. Collaboration and communication. Fostering a culture of collaboration and communication among development, operations, and QA teams to ensure alignment and shared ownership of CI/CD processes. In conclusion, continuous integration and continuous deployment are essential practices in modern software development, enabling teams to deliver high-quality software more efficiently and reliably. By embracing CI/CD principles, organizations can accelerate their development cycles, improve collaboration, and deliver value to users more effectively. Containerization and orchestration have revolutionized the way modern applications are developed, deployed, and managed. In this extended discussion, we will explore containerization technologies such as Docker and container orchestration platforms like Kubernetes, their significance, architecture, benefits, and best practices. Understanding containerization. Containerization is a lightweight virtualization technology that allows applications and their dependencies to be packaged into portable, self-contained units called containers. Each container encapsulates the application code, runtime environment, libraries, and dependencies, ensuring consistency and reproducibility across different environments. Benefits of containerization. 1. Portability. Containers are platform independent and can run consistently across different environments, including development laptops, test servers, and production clusters. 2. Isolation. Containers provide process-level isolation, ensuring that applications and dependencies are encapsulated and isolated from each other, leading to improved security and stability. Number 3. Resource efficiency. Containers share the host operating system's kernel and resources, resulting in lower overhead and faster startup times compared to traditional virtual machines. Understanding Docker. Docker is the leading containerization platform that simplifies the process of building, distributing, and running containerized applications. Docker provides tools and APIs for creating, managing, and orchestrating containers, making it easier for developers and operators to work with containers. Docker architecture. 1. Docker engine. The Docker engine is the core runtime environment responsible for creating, running, and managing containers. It consists of the Docker daemon Dockerd and the Docker CLI, Docker. 2. Docker image. A Docker image is a lightweight, standalone, executable package that contains everything needed to run a specific application, including the application code, runtime environment, libraries, and dependencies. 3. Docker container. A Docker container is an instance of a Docker image that runs as a standalone process isolated from other containers in the host system. Docker use cases. 1. Microservices. Docker enables the adoption of microservices architecture by providing lightweight, isolated containers for individual services, improving scalability and agility. 2. DevOps Practices. Docker facilitates DevOps practices such as continuous integration, continuous delivery, and infrastructure as code (IAC) by providing consistent environments for development, testing, and production. 3. Hybrid cloud deployments. Docker simplifies hybrid cloud deployments by providing a consistent platform for packaging and deploying applications across on-premises data centers and public cloud environments. Understanding Kubernetes. Kubernetes is an open-source container orchestration platform that automates the deployment, scaling, and management of containerized applications. Kubernetes provides a rich set of features for scheduling, networking, storage, and monitoring, allowing organizations to run containers at scale with minimal manual intervention. Kubernetes architecture. 1. Masternode. The Kubernetes masternode is responsible for managing the cluster's control plane components, including the API server, scheduler, and controller manager. 2. Worker node. The Kubernetes worker node hosts the containers and runs the workload pods. Each worker node runs a Kubernetes agent called kubelet, which communicates with the master node and manages the container's lifecycle. Per pod, a pod is the smallest deployable unit in Kubernetes, representing one or more containers that share the same network namespace and storage volumes. Pods are scheduled and managed by Kubernetes and can be horizontally scaled to meet application demands. Kubernetes use cases. 1. Container orchestration. Kubernetes simplifies the orchestration of containerized applications by automating deployment, scaling, and management tasks, leading to improved resource utilization and application availability. 2. Multi-cloud deployments. Kubernetes provides a consistent platform for deploying and managing applications across multiple cloud providers and on-premises environments, enabling organizations to embrace multi-cloud strategies. 3. Service discovery and load balancing. Kubernetes provides built-in support for service discovery and load balancing, allowing applications to communicate with each other seamlessly and distribute traffic across multiple instances. Best practices for containerization and orchestration. 1. Container image optimization. Optimize container images by minimizing the number of layers, removing unnecessary dependencies, and using lightweight base images to reduce image size and improve startup times. 2. Resource allocation. Define resource requests and limits for containers to ensure optimal resource utilization and prevent resource contention in Kubernetes clusters. 3. High availability. Design applications for high availability by deploying multiple replicas of critical services across different availability zones and regions, leveraging Kubernetes' built-in features for load balancing and failover. 4. Security and compliance. implement security best practices such as image scanning, vulnerability management, network segmentation, and role-based access control are back to protect containerized workloads and comply with regulatory requirements. 5. Monitoring and logging. Implement monitoring and logging solutions to track container performance, resource utilization, and application health, enabling proactive troubleshooting and optimization. DevOps practices have emerged as a transformative approach to software development and IT operations, aiming to break down silos, streamline collaboration, and accelerate the delivery of high-quality software products. In this extended discussion, we will delve deeper into the principles, methodologies, tools, and benefits of DevOps practices, focusing on how they enhance agility, reliability, and efficiency in modern software delivery pipelines. Understanding DevOps. DevOps is a cultural and organizational movement that promotes collaboration, automation, and continuous feedback across development, operations, and other stakeholders involved in the software delivery lifecycle. At its core, DevOps aims to align the goals, processes, and tools of development and operations teams to deliver value to customers more rapidly and reliably. Key principles of DevOps. 1. Culture. DevOps emphasizes a culture of shared responsibility, trust, and continuous improvement, fostering collaboration and communication among development, operations, and business teams. 2. Automation. DevOps advocates for the automation of repetitive tasks, such as code deployment, infrastructure provisioning, and testing, to eliminate manual errors, reduce cycle times, and increase productivity. 3. Measurement. DevOps encourages the use of metrics and feedback loops to measure the performance, quality, and efficiency of software delivery processes, enabling teams to identify bottlenecks and areas for improvement. 4. Sharing. DevOps promotes the sharing of knowledge, best practices, and tools across teams, creating a culture of transparency, learning, and innovation. DevOps methodologies. Continuous integration, CI. Continuous integration is a development practice where developers frequently integrate their code changes into a shared repository, followed by automated builds and tests to validate the changes. CI enables early detection of integration issues and ensures that the codebase remains stable and deployable at all times. Continuous delivery, CD. Continuous delivery extends CI by automating the deployment process to production-like environments, allowing teams to release software updates to customers quickly and reliably. CD emphasizes the use of automation, deployment pipelines, and release management practices to reduce lead time and increase deployment frequency. Infrastructure as Code, IAC. Infrastructure as Code is a DevOps practice that involves managing and provisioning infrastructure resources using machine-readable definition files, such as code or configuration templates. IAC enables the automated provisioning, configuration, and management of infrastructure resources, leading to greater consistency, repeatability, and scalability. DevOps tools and technologies. Configuration management. Tools like Ansible, Chef, and Puppet enable teams to automate the configuration and management of infrastructure resources, ensuring consistency and reliability across environments. Continuous integration, continuous deployment, CI/CD tools. Platforms like Jenkins, GitLab CI/CD, and Circle CI provide automation capabilities for building, testing, and deploying software applications, facilitating the implementation of CI/CD pipelines. Containerization and orchestration. Technologies such as Docker and Kubernetes enable teams to package, deploy, and manage applications in lightweight, portable containers, providing scalability, agility, and resource efficiency. Monitoring and logging. Tools like Prometheus, Grafana, and ElkStack enable teams to monitor application performance, track system metrics, and analyze logs to identify and troubleshoot issues proactively. Benefits of DevOps practices. Faster time to market. DevOps practices enable teams to deliver software updates and features to customers more frequently and predictably, reducing time to market and increasing business agility. Improved quality and reliability. By automating testing, deployment, and monitoring processes, DevOps practices help teams detect and address issues early in the development lifecycle, leading to higher quality and more reliable software. Enhanced collaboration. DevOps fosters collaboration and communication among development, operations, and other cross-functional teams, breaking down silos and promoting shared ownership of software delivery. Increased efficiency and productivity. Automation of repetitive tasks, such as infrastructure provisioning and deployment, frees up time for developers and operators to focus on innovation, creativity, and value-added activities. Greater scalability and resilience. DevOps practices enable organizations to scale their infrastructure and applications dynamically, respond to changing demand, and recover quickly from failures, ensuring business continuity and customer satisfaction. And that brings us to the end of this lesson. But there's so much more to discover. In the next video, we'll delve into monitoring and performance management. Stay tuned.